we are ready to continue lecture notes 7. I'm talking about point estimation. So now we've seen 3 methods for finding point estimators: the method of moments, the maximum likelihood estimator, and the Bayes estimator. Any questions about these? Okay, so we did one example of Bayes estimator. I just want to mention another one because it's so common. Which is the normal. And for the moment, let's take sigma squared known. So this is some fixed known number. The parameter is mu. To get a Bayes estimator, remember you have to pick some sort of prior distribution. We still haven't really talked about why you pick one prior over another. But if you want a Bayes estimator for mu, we have to pick some prior, and a common choice would be to take mu itself to have a normal. And to specify a normal, I have to specify 2 parameters that are mean variance of that. So I'll put those out. These are not parameters, these are numbers equated to specify the prior. So, remember the trick we did with the likelihood about expanding rewriting the likelihood in terms of x bar. This is another one of those cases where you need to do the calculation once yourself to see what's going on, because there's a kind of a trick here. If I multiply this out, this is a little bit messy. Remember, this is basically the this is the likelihood times the prior. We saw with the red right here. The prior now looks like this. So here's a good calculation for a homework assignment. Definitely, everybody should have done this once. If you've never done this before, you should do this, which is how do I combine this? I want this to look like something familiar. Well, I'm going to tell you the answer. It's going to look like a, I think it's going to look like a normal. So it's got to look like, somehow I've got these 2 mu's here. I've got to get them to one expression. And the way you do this is you bring these 2 terms together, and you do remember from high school, you do the squares, the squares, you get a quadratic, and so on. And you try to write it as mu minus something squared plus something. So it's a little bit annoying. It's a little bit tedious, but it's very simple. And I'm just going to tell you the answer, but if you've never done it before, you should definitely do this. So this is going to end up being e to the minus mu minus all this. Okay, so what I'm leaving out again is some simple but annoying algebra that takes you from here, which is rewriting this mu minus something squared over something squared. And once we see that the posterior distribution thinking of mu as a random variable is a normal, with some mean A and some variance B. In particular, it turns out that what you get is that A is x bar times all this stuff plus this. And so this is going to be the Bayes estimator, because so this is mu hat, because it's the mean of the posterior. And it looks kind of messy, but really what you have here is the prior variance, and then the variance of x bar. So it's very intuitive only. And again, it's a convex combination of the MLE and the prior mu. And for n large, you see this term disappears, and you just get it. So it might look messy, but it's actually very intuitive. So now we've seen 2 examples of Bayes estimators, the Bernoulli, the normal. There's maybe a bit of messy algebra involved, but the principle is very simple. Just take the likelihood, multiply it by some prior, and find some summary of this posterior distribution. For now, we're using the mean of the distribution. Later on, we'll consider other summaries. So We have lots of estimators now. Oh, question, yes.
Do Bayes estimators relate directly to max estimates?
Yes, if you took the mode of the posterior instead of the mean, that's called a MAC. So there's more than one way to get an estimator from the posterior. For now, I'm just using the mean because that's a common one, but it's not the only one. Any other questions? What we now have is kind of an embarrassment of riches. We have infinitely many estimators because we have the method of moments, we have the maximum likelihood estimator, and then we have the Bayes estimator. But the Bayes estimator, there's a different Bayes estimator for every prior distribution, so there's infinitely many Bayes estimators. So what we need is some way to say, well, what's a good estimator? And the way we're going to attack that question of deciding what's a good estimator is in steps. We're going to start, first of all, with something very simple, which is just talking about something called the mean squared error of an estimator. That's a property of all these estimators, and it's a first step towards understanding the properties of the estimator, but it doesn't completely solve the question of what's the best estimator. It's just the first step. The second step, which will be in the next notes, is something called Minimax Theory, which gives us a formal way to talk about what the best estimator is. And then the notes after that talk about large sample theory. That is, how do we talk about the best estimator when n is large? Or more generally, what's the properties of this estimator as n grows? Things get a much cleaner in that case. We get a much clearer picture about what's going on. So those are the steps. We're going to start with one property called mean squared error. Then we're going to go to a more general thing called minimax estimation. And then we're going to look at the asymptotic theory after that. So I'm on page 6 of the notes here. So the mean squared error is just one way to say how good is my estimator. And as we'll see, there's lots of other ways to do this, but this is a good way to start. And what is the mean squared error? Well, remember that theta hat is a random variable, right? It depends on all of the data. So one way you might say how good is this estimator is I might look at the expected value, theta hat minus theta squared. Just how far is the estimator from the true value? And in some sense, if we just approach this heuristically for now, if that's small, that would suggest we have a good estimator. If that's big, it would suggest we have a poor estimator. But going from that intuition to the formal theory is what the next set of notes will be about. Let's just remind ourselves really what this means, because we're talking about a joint distribution here. Don't forget theta hat depends on x1 to xn. And when I say the expected value, I mean the expected value with respect to the joint distribution. So that's p of x1, assuming IID. Okay, that's what the mean squared error is. So, how do we actually compute this? Are we actually going to do this integral? No, we're rarely going to actually have to do this integral. There's some shortcuts here. The first thing is a very, very simple but important equation which shows up in statistics and machine learning all over the place, which is called the Bias-Variance Decomposition. So the mean squared error can be written in the following form: bias squared plus variance squared. What do I mean by that? The bias is defined to be the mean of the estimator minus the truth.
Bias squared plus variance, or bias squared plus variance?
Oops. Thanks. So the bias is just the mean of the estimator minus the truth, and the variance is the variance. Variance means. And the reason for writing it that way is, first of all, conceptually this is very useful because, as we'll see later in the course in 702, a lot of things involve trading off the bias. Sometimes things have high bias, with small variance, and then you try to make the variance bias smaller and the variance gets bigger. Often there's like a tug of war between the bias and the variance, so that's something we'll have to deal with eventually. But for now, it's just a useful decomposition because it's often easy to compute these separately. And so think of it as a way to compute things. Let's actually prove this. It's very simple. So let's give a name. Let's say M is the mean of theta hat. number. Yeah.
Just explain this bias and variance questions. Why does MSE have something constant?
Oh, maybe I should, yeah, it probably was a little bit confusing. Sometimes there isn't such a trade-off. I was kind of thinking a little bit ahead that in complicated situations like classification, for example, very complicated, or regression, complicated models typically have both bias and variance, and there's like a trade-off between when you're trying to find a good predictor between bias and variance. But that's actually a little bit outside of what we're talking about now. Maybe I shouldn't even mention it because in this context it's pretty confusing. So we'll come back to that. All right, let's just do the two-line proof here of that result, which is that the MSE is the expected value of theta minus theta squared. And all I'm going to do is add and subtract m. And so now I get this squared. Then the expected value of this squared. But look, when I square this, so I got this squared plus this squared. This is m minus theta squared. Those are constants. M is a constant, theta is a constant. So I don't need the expected value. I can just write that as. And now I have the 2 times the cross product term, theta hat minus m, times m minus theta. Again, m minus theta comes out front because that's a constant. And if we look at this, well, what's the expected value of theta hat? M, so this is 0. And we're done. This is the definition of variance. Right? This is quantity minus its mean squared, expected value. And this is the bias. This is the expected value minus the truth, so that's the bias. So it's very simple, but incredibly useful. Now, there are some estimators we'll see, especially in parametric statistics. Sometimes we'll have an estimator that has 0 bias. If the bias is 0, then the MSE is just the variance. And 0 bias is not that important. What matters is the sum of these two things. You could have a little bit of bias, and you could have quite a bit of bias and small variance. It's probably a good estimator. So there was a time in statistics where people talked a lot about unbiased estimators. That means things with 0 bias. And there was a lot of focus on that, like in the 50s or something like that. And these days, people don't consider it that important because what really matters is the combination of bias and variance. So let's go back to the normal. And let's consider estimating mu and sigma squared. So we might take mu hat to be x bar. There's an estimator for you. That's method of moments estimator. That's the maximum likelihood estimator. How about S sigma hat squared? Well, there's lots of different estimators we could choose, and you know, we saw that the MLE was this, but now few people raise the point that people often do this estimator, and the reason is this. This makes this unbiased. You can check. There's an exercise that if I do it this way, it's sigma squared. Now again, that's not really that important, as I just explained. If you divide it by n, you get a little bit of bias, but so what? That doesn't really change things that much. But you will see in a lot of textbooks that instead of using the MLE, they use this estimator, and the reason is they want it to be unbiased. I really think that's more of a historical thing than anything else. But I don't care whether you want to divide by n or n minus 1. It doesn't matter. It's not going to make much difference. Okay? Pick your favorite estimator. Once you have 10 observations divided by n or n minus 1 is not going to make much difference. Let's look at these things. Let's look at this estimator. Let's compute the MSE. First of all, what's the bias? 0. So the MSE is simply the variance. And so that's just sigma squared over n. So that's pretty good. That's going to 0 pretty fast for them. And not surprisingly, the MSE depends on sigma squared. If sigma squared is small, we're going to be able to estimate mu better. And this one I'll leave as, this one's a bit tedious. If you want to have some fun this weekend. This one's not easy, so I'll just tell you what it is. If you had divided by n instead of n minus 1, you get a slightly different expression, but it won't be very much different. It doesn't change the MSE. What I want you to notice about both of them, though, is that the MSE is going to 0 as n gets bigger, which means in some sense we're estimating the parameter better. And at what rate is it going to 0? You can see they're both big O 1 over n. Remember our big O stuff? This is kind of characteristic of many parametric problems, that the mean squared error goes to 0 at a rate like 1 over n. What we'll see later in the course when we talk about non-parametric methods, where we don't assume parametric models, is that it's not always possible to get estimators that converge, whose MSE converges so quickly. It might converge much slower. So 1 over n is kind of characteristic of many parametric, some non-parametric problems, but many parametric problems. So it's good to know how to compute the MSE of an estimator, but it doesn't quite answer our question, right? So I can compute this, but it still doesn't tell me, if I was considering another estimator here, it might not be obvious still which estimator to pick. And in particular, let's look at this one. The MSE, the mean squared error, actually depends on the parameter I'm estimating. If you gave me a different estimator, and it had a slightly different MSE, maybe say it was, I don't know, sigma to the cubed over n minus 5 or something like that. How would I decide which one's better? It's not obvious. To compare those two MSEs would involve looking at the true value. We don't know the true value. That's why we're estimating. So being able to compute the mean squared error is a very useful thing, but it hasn't quite solved the problem for us saying what the best estimate is. Okay, that's what we're heading for. So this computing MSE is only a first step. Good. So any questions? Yeah.
Where S is the sigma factor. The estimation of.
I should have said that. This is. There's two different symbols there.
Why, can you understand why this is not enough to compare to estimators? So you have to
Well, look at the, think about it this way. The MSE is a function of the parameter.
Okay.
So in general, actually, if I ask you, let's think about this more generally. Suppose I ask you to compute the MSE. Actually, we got lucky here because there's no mu in this formula. But in general, the thing you're estimating could show up in this formula. So when I say compute the MSE, it might be a function. It might be something that changes with theta. Now suppose I have an estimator and I say, here's my mean squared error. It's really a function of theta. Now suppose you say, oh, I have a better estimator. And so you give me your estimator, I compute its MSE. It's also a function. Maybe it looks like this. Now I ask you, which is a better estimator? Okay. So we're going to talk about that right now. So I mentioned that there was this fixation for many years in statistics about unbiased estimators. So I included a little taste of history for you here. I'm not going to go through this because I really don't think these days it's that important. But it's only half a page long, so you should just look through it on your own. You'll look through some older textbooks and you'll see there's long chapters called Best Unbiased Estimator. And the idea that they're trying to do is this. They're saying, suppose we restrict ourselves to only unbiased estimators. Estimators whose expected value of theta hat is equal to theta. So there's no reason to restrict ourselves to those estimators. Perfectly good estimators that are biased. But suppose we did restrict ourselves. Then we can answer the question, which of those estimators has the smallest variance? That might be a way to define the best unbiased estimator. And there's oodles of theorems about this, and there's all kinds of stuff. I actually reproduced one of the theorems there for you. It's called the Kramer-Rao lower bound. What it does is it gives you, You're looking for the uniform minimum variance unbiased estimator. How's that for a mouthful? UMVUE. That's already a sign that's not a good theory. That's like a really bad acronym. But there's oodles of theorems about this. The reason why, again, I don't emphasize it and go through it in detail, because I really don't think it's that useful, except for maybe historical reasons. So I'm not going to go through that, but it's there if you want to look at it. And there's also another famous theorem that's there for you called the Rao-Blackwell theorem. I just think it's so important that I felt like I should put it there, even if we don't use it that much, which says that, basically what the Rao-Blackwell theorem says is, suppose you are interested in unbiased estimators, and suppose I have some unbiased estimator, let's just call it W. But suppose you notice that this thing is not a function of the sufficient statistic. Remember we said that somehow everything should just be, like a sufficient statistic should contain all this information. Suppose this was a function, for example, in the normal, it was a function of x bar and x3. Somehow it seems like having x3 in there isn't really helping you. And what the Rao-Blackwell theorem says is if I can take the expected value of W given the sufficient statistic, and this is still an estimator. Remember, an estimator can't depend on the parameter, it can only depend on the data. And this is guaranteed to only depend on the data, not on the parameter. Why? Because when you condition on the sufficient statistic, the distribution doesn't depend on theta anymore. So this expected value will be some function. It'll be something you can compute from the data, but it won't depend on theta. In other words, this defines a new estimator. And you can show that by conditioning on the sufficient statistic, you must have improved the estimator. You automatically got another unbiased estimator with smaller variance. It explains one of the reasons why people were so interested in sufficient statistics. Somebody comes up with an estimator, it's unbiased, but it's not a function of the sufficient statistic, so just compute its mean given the sufficient statistic, you get a new estimator and it's got smaller variance. Okay, so if this was 20 years ago, we would now spend 6 lectures proving theorems about uniform minimum variance unbiased estimators and doing Rao-Blackwell calculations and so on. And I think there are still statistics departments that do that. I don't do it because I just really think it's not that unbiased estimators are just not that interesting. And I just don't think in modern machine learning and statistics it's really that important. Okay, so if you feel like you really want to know that stuff, by all means, you can find it out there. It's very easy. It's even on Wikipedia, so you can learn it yourself. But we're not going to spend class time going over all that unbiased estimator stuff. Instead, I want to move on to what I think is more useful, which is how do we compare these estimators? And this brings us to Minimax Theory. Our goal here.
What's the question?
Oh,
Hi. So are we ever going to go back to the end of lecture 6? There was that one section.
oh, you're right. Yeah, eventually. I have to figure out when the right time is. It's more of a philosophical kind of a point, so we have to be all in kind of a philosophical mood and then we'll go back to it. But thank you for reminding me. All right, I want to get to this question about what's the best estimator, or if you're doing prediction, what's the best predictor? And this is something which is very current, interesting. We're going to use something called Minimax Theory. And this used to be sort of something restricted to statistics, but now you see it in ML all the time. If you look at NIPS papers, you'll see a lot of papers about Minimax Theory now. Because it's a way to try to say, at least theoretically, under certain conditions, when can I say one estimator is the best estimator in some sense? That's our goal, is to say something about optimality, in other words. What's the optimal estimator? Now, it's really more of a theoretical concept. I'm not saying that people are necessarily in practice going to choose estimators using this theory, but it's a way of understanding why estimators are good or what makes them bad and so on. In this class, we're really just going to I'm going to give you a little introduction to Minimax Theory. The theory gets a little bit complicated, so what we do is, for those of you who take 702, we do a whole set of lectures on Minimax Theory where we go into it in much more detail. Here I just want to get you, what is the basic idea, and what is the one sort of main important theorem you should know. Right? So it's really the concept I want to introduce to you. So the question we have is, I have data from some distribution. I have a parameter I want to estimate. How do I even define what it means to be the best estimator? So, to start off with, we have to decide, well, what do we mean, first of all, by a parameter estimator being close to the truth? And that's really problem dependent. There's no answer to that. The way this theory is going to work is, if you tell me what you mean by closeness, then I'll tell you what the optimal estimate is. But you get to decide what you mean by close. It's going to be very problem specific. So this is measured with something called a loss function. And we've already used one. So probably the most common loss function is called squared error loss, which is the name implies this. That's what we just used a moment ago when we defined the mean squared error. We were using the squared distance as a measure of loss. But there's lots of other loss functions you can use. I've listed some here in the beginning of lecture notes 8. You could use the absolute value. And there's many, many other loss functions you can use. For example, in classification, when you're trying to predict a binary outcome, you're trying to predict some y1 or y0, and usually you know what we do in classification is we'll have some covariates, and we'll have a function, a classifier, which outputs a 0 or a 1. And the most commonly used loss function, not the only one, but the most commonly used one, is the 0-1 loss, which is the loss is equal to 0 if you guessed right, if h of x equals 1, and 1 otherwise. So that's called the 0-1 loss. The point about Minimax theory is that it's going to work for any loss function. It's very general. So give me any loss function, and now we can talk about what it means to have an optimal estimator with respect to that loss function. Yeah.
Do these loss functions depend on the data as well, since they have theta cap but no expectation over the data?
That's right. This loss function, this loss is a random quantity. That's correct, because it's got theta hat in it. Theta hat's random. That is the value, I should say the value of the loss function is random. In fact, that leads to the next definition, which is the risk. Which, I'll write it, what did I write here? This. Which is exactly taking the expected value of the loss. In other words, I take the loss function. I see that sometimes I'm writing theta hat, sometimes theta hat. They mean the same thing. Follow up on the point that was just raised, the loss depends on the data when we evaluate it. The risk does not, because we're integrating out the data, but it still depends on the parameter of theta. It's a function of theta. In fact, if I take L2 loss, what's the risk? Value of the loss. It's the mean squared error. So now we see the mean squared error is actually a special case of a more general concept, which is the MSE is the risk when we're using L2 loss, but if we use a different loss, we'd have a different measure of risk. And the key thing here, again, is that this risk function, if you give me an estimator, I can compute it, but it's a function of theta. Who knows what it looks like? And if you give me another estimator, it might look like this. So we still have this variability problem. So now I can tell you what a minimax estimator is, which is, let's just use this board again. I'm going to say, here's what we're going to do. A lot of times what we're trying to do is protect ourselves from the worst case. We don't know the true value of theta, so we're going to look at the worst case. I'm going to look at the maximum risk. This is the worst this estimator can do. And for this one, I don't know where's the maximum, like here. I'm going to say this estimator is better than this estimator. This estimator sure is better than this estimator because its maximum is smaller than this. I'm going to use the maximum of the risk to define the quality of the estimator. So I want to minimize the maximum. Hence the name Minimax. So the Minimax risk the definition of the Minimax risk is this. I'm going to look at the maximum, the supremum, the maximum of that function. So you give me an estimator, theta hat, and I'm going to compute that function and take the maximum. But now I want to ask, what's the smallest I can make that over every possible estimator? So I want to take the minimum or the infimum over all possible estimators. That's called the Minimax risk. The Minimax risk is in some sense a measure of how difficult a problem is. If you ask me how hard is it to estimate a covariance matrix in high dimensions, or how hard is it to do classification when there's no linear separator and blah, 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 blah. How do you quantify the difficulty of the problem? One way to do it is to compute this Minimax risk. This is sort of the best you can do. And then an estimator which achieves this. So if I can find an estimator whose maximum risk is equal to this number, then I've achieved the Minimax risk. So theta hat is Minimax if its maximum risk is equal to this. If the maximum of its risk, because in general the maximum risk of any estimator is going to have to be bigger than or equal to this. But if I can get it equal to this, then I have a Minimax estimator.
Would you ever want to put a prior on theta?
That's a great question, which is why maybe we want to average this instead of taking the maximum, and we will talk about that in great detail. That's a very good question. What we're going to see, just to jump ahead a bit, is if I integrate this instead of taking the maximum, we get back Bayes estimators. And the Bayes estimator for a specifically chosen prior is exactly the Minimax estimator. In fact, that's how we compute the Minimax estimator. It's the Bayes estimator for a particular prior. And we'll make all those connections probably next week. Okay, so you can see though that there's some difficulties here, which is how do I even find this quantity? Because I'm minimizing, for any one estimator, I can imagine, let's suppose we're using L2 loss. By the way, if I don't tell you the loss function, let's just assume it's always L2, unless I say otherwise. It's just a very commonly used loss function. You give me any estimator, and computing this is probably not so bad. I mean, if this is L2 loss, then this is the MSE. I have to compute the bias, the variance. It's probably doable. So I can get this function. Now I say minimize it over every possible estimator. Every possible estimator. There's infinitely many estimators in the universe. So how am I going to find that minimum? That's not obvious how to do this. Luckily, there's some tricks people have come up with over the years to figure out what this quantity is. And then I have to say, can I find an estimator which achieves it? What is the Minimax estimator? And in some problems that's easy, and in some problems it's very difficult to figure out what this optimal estimator is. All right. So, any questions so far? Make sure the concept that we're aiming for is clear. Yeah.
So all this is done by the assumption that the model is given.
That's right. So we're doing this under a given loss function and a given model. That's correct. Later, like when we do non-parametrics, the model might be very large. It might even be all possible distributions. But there is some set of distributions we're considering. For now, again, we're sticking to parametric models. Any other questions? Yeah.
Are we ever able to compute these precisely? Or
Well, we're gonna
are there
compute it.
fancy things like estimators of RM?
Yeah, no, we're going to compute this. Not always can we compute it, but a lot of research papers are written about trying to approximate it because it's very hard to compute it exactly. But in some, as usual, in simpler examples, we can compute it exactly. All right, but just to get across, again, this idea that what we're trying to do is compare these risk functions. I just want to look at a couple of simple examples before we proceed. So I'm looking at example 3 on page 2, and I want you to think about this for a second. Let's take a very simple problem. I have a single observation from a normal with mean theta and variance 1. All right. And I want to consider two estimators. So you go, well, I've taken statistics. I know what estimator to use. I'm in only one observation. I'm going to use X. That's the MLE. But you have a friend in engineering. Any engineers here? Okay, in history. and your friend says, I'm just going to take the estimator 3. Just always 3. Now, you're kind of laughing at your friend there. Your friend says, hey, this is really easy to compute. It's very scalable. I can do this in very high dimensions. So, big data and everything. I got no problems. And you say, no, but this is going to have terrible properties. So let's work out the risk function. So the first one, and let's use L2. Let's use L2 loss. So the risk is the mean squared error. Well, we know what this is. It's 1. It doesn't even depend on theta. So let me plot the risk. In this case, it's a constant. It's equal to 1. It doesn't even depend on theta. Now your friend, let's look at their. Well, I don't even need, it's the expected value of the estimator minus theta, but theta hat isn't even random. This is just 3 minus theta squared. And if we start at 3, my friend has 0 risk, actually. I'm not drawing it very well, but that's up to artistic error. What's your friend's risk function? And so your friend will correctly point out that if the truth happens to be near 3, he's actually doing much better than you are. You'll probably respond with, yeah, we don't know where theta is. And if you're far from 3, your estimator is a disaster. And you can see instantly, of course, in this example, if I look at the maximum risk, your friend's estimator is much worse than your estimator. In fact, we're going to see for a normal that x bar is in fact minimax under virtually any loss function. Let's look at a little more subtle example, which might be a little bit more surprising. And it's our good friends at Bernoulli, which up to now, Bernoulli always sort of one of the easiest examples. But now we're going to see some kind of counterintuitive behavior. So let's see what happens for Bernoulli's. I'm going to take n coin flips. Alright, so again, let's imagine 2 people. So you say, well, I'm going to use the MLE. So I'll find my estimator, and we know what that is. It's x bar. So we'll use squared error loss. So first of all, what's the bias of that estimator? 0. So the MSE is just the variance. So what's the MSE? Right. Minus P over here. So let's draw that. It's actually, it's like this, right? You actually do really well when P is near 0 or 1. And in the middle, you're still doing pretty good, because look, this is at most a quarter. So this is always less than 1/4n, which is pretty small. So I've drawn it like it's big, but the truth is, even up here, it's pretty small. However, your friend says, I'm going to choose this estimator. I'm going to pick two constants, alpha and beta, and I'm going to use this estimator. Does this look familiar? It's the Bayes estimator for a particular ply, for a particular choice of alpha and beta. So let's evaluate this. How am I going to evaluate this? Well, it's not so bad. I have to compute the mean and variance of this side. So the mean is not so bad. If I take the mean, as everything's a constant, this becomes n times p. And the variance, again, is not so bad. The variance of this would be 1 over alpha plus beta plus n squared. Comes the variance of this would be np1 minus p. So we can get the bias, and we can get the variance. I actually wrote out all the details for it if you want to see it there. And what you get is the expressions on page 3. It's just kind of a mess. Okay, so I'm not going to go through here, but it's pretty simple. It's kind of complicated. But then your friend has a really clever idea. Remember, every alpha and beta defines a valid Bayes estimator. You can pick any alpha and beta he wants. So I'm going to pick alpha to be equal to beta to be equal to the square root of n over 4. That's a pretty strange looking estimator. But it's an estimator. You know, I just plug that in there and I have an estimator. And if you plug that into the MSE, it turns out the risk becomes n over 4 plus n plus root n squared. And actually, it doesn't depend on p anymore. That's the really interesting thing. And if you plot it, I actually have a plot of this on page 4. It looks like this. Well, it should stop at 0 and 1. So let's not get carried away here. Now, from the point of view of maximum risk, who has the better estimator? Your friend does. His maximum risk is here, yours is up here. You might want to argue, however, that you're beating him in this region. However, we have to be careful about arguments like that because we don't know P. And the way I like to think about pretty much most of statistics is we're trying to protect ourselves from the worst case. We should always assume nature's out to get us. I'm pretty sure it is. So, you know, from the Minimax point of view, we haven't shown what the Minimax estimator is, but the Minimax point of view, this one's starting to smell better than this one. In fact, we'll see later on, this is actually the Minimax estimator for this problem. So you can see that the Minimax estimator can be very, very counterintuitive.
How did you compute this?
It's done in the notes. It's just computing the mean and the variance. It's just algebra. All right, but there's still a mystery here, which is I keep pulling estimators out. How about this one? How about this one? If I actually want to get the Minimax estimator, I'd have to think of every estimator there is in the universe, compute its risk, plot it, find the maximum, and keep doing it and finding the minimum one. That's going to be a bit of a problem, right? So we need to be more systematic somehow about this. And fortunately, there are some ways of getting to this, and one route is through the Bayes estimator. Now, warning, the word Bayes estimator we used before to be the mean of the posterior. That was actually a very specific type of Bayes estimator. Now we're going to use the word Bayes estimator for something much more general. And somebody asked about this. They said, look, take that risk function, and instead of using the maximum to summarize it, why don't we put a prior distribution down and integrate it, integrated risk. So let's try that. I'm going to call the Bayes risk to be the integral of this risk function. But again, I have to pick some prior I called the prior, for some reason, a pi thing. And I need to give this quantity a name, so I'm going to call it B for Bayes. But let's remember that it depended on the choice of prior, so I'm going to put the pi down here. So instead of using the maximum, I'm using the average. It reduces it to one number. Okay. Now, I can do this for any estimator again. I can say, for any estimator you give me, I can compute its risk function and integrate it over theta and get this number. And I can ask again, can I minimize that? Instead of minimizing the maximum, I can minimize this thing. That's called the Bayes estimator. So that's now our notion. When I say Bayes estimator, I mean this more general notion of Bayes estimator. It's the estimator that minimizes that quantity. Theta hat, maybe I should write sub pi to remind you there's a prior there, which minimizes it's prior dependent. Now it might seem like we haven't gotten very far because before I was trying to minimize the maximum risk, now I'm trying to minimize the average risk. It still seems like I have to try every possible estimator to see what does that. But what I'm about to show you is that that's not true, that in many cases we can compute this very easily explicitly. Okay. And then the next trick is that if we choose pi carefully, it also happens to give us the Minimax estimator. So oddly enough, the route to getting the Minimax estimator is often first compute a Bayes estimator and make sure we pick the prior to certain line, and then we get the Minimax estimator. All right, so let's see, how do we compute these Bayes estimators? Why is it that they're easier to compute than computing the Minimax estimator directly? Before I proceed, though, I've hit you with a lot of definitions. So let me just see, are there any questions? Yes?
These are all still functions of n, right? Shouldn't we consider the variation like for a large n?
Are these functions of n? Is that the question?
Yeah, I'm saying these graphs that we're getting, they're still functions
Oh,
of n. So
good point. So these, if I were to draw that picture for you as n changes, they would change a lot. They would all get smaller. Well, hopefully they would all be going down as n gets bigger, yes.
but can't the relation between which estimator is better also change as n changes?
Absolutely. So when we talk about, that's absolutely correct. So another thing we're interested in, this is something we talk about more in 702, is if I compute the minimax risk, for example, hopefully this is going to 0 as n gets big. But at what rate does it go to 0? That's a really important question. And so we won't talk about that so much in this class. We're going to see that, again, for parametric problems, typically this is going to be like 1 over n. And in non-parametric problems, it's typically going to be 1 over n to some power, but it typically won't be 1. It'll go slower. And in CS, people often turn this around and call this the sample complexity. Here I'm asking, how fast does the risk go to 0? But you can turn it around and say, how big a sample size do I need to make sure the risk is less than epsilon? That's called the sample complexity. That's often how things are done in theoretical CS. It's just another way of talking about the risk, the minimax risk. So yeah, the speed at which it goes to 0 is definitely an important quantity. We probably won't talk too much about that in this class. Any other questions? Yeah.
So, I didn't phrase my previous question correctly. How do we set A and B square root n over 4? We just cut it so that it doesn't depend on
Yeah. The question is, how did I know to pick this choice? Yeah, we'll get to that. It absolutely was, it was not an accident that I did it. So let's talk about, oh yes.
How method that is faster than 1 over.
I'm sorry?
A method that is faster, go to 0, going to 0, then 1 over.
Faster than 1 over n?
Yeah.
There are cases when the risk can go to 0 faster than 1 over n, but they're not common. They're sort of irregular cases usually. Typically 1 over n is the best you're going to do. There are some exceptions. 1 over n sort of means an easy problem. Okay, so what's going to happen, let me tell you, we'll pick this up next week, which is that we're going to finish this section. It's a little bit subtle, this Minimax stuff, and we'll probably try to finish it Monday or Wednesday. Then we're going to start talking about what happens when n is large. Things simplify quite a bit to get a lot neater, and that'll come after we do the big stuff. Okay, so we'll see you next week.
Friday.